but here we go. Does anybody have any particular questions before we start? We're going to do some more of these examples. I want to point a couple things out. First and foremost, what is this? This is lecture. What is this? Lecture number 32, right? And so today is April Fool's Day, although no one is, I'm sure, enjoying that. Here we go again. Maybe standing. Standing could be a problem as I adapt. All right, so here's what's kind of important for us to understand. So last class, we introduced cylindrical and spherical coordinate systems. And how to integrate using them. Now, one of the things I want to point out, because this is important, we use these words, big theorems, last class, if you look at the lecture, because I don't want to bog you guys down with all this scary theorems, these scary statements of why this stuff works. So what you should understand is that it's not that I don't think you can do it, but we omitted the statements. Of the quote unquote theorems and opted for examples. So now if you'd like to know the big theorems, if you'd want to understand the specific sort of language of how these things are, the details of these things are in the book, if you so are inclined, or you can find them on the internet. Okay, so let's do an example of spherical before we do some sort of applications. Does anybody have a question at all? I mean, again, it's not that I don't think you guys are bright enough. It's just that I don't know if it's worth our time, especially being that we're doing this sort of on the internet, sort of like a live stream or whatever you want to call this. I don't know if it's worth our time to write down these scary statements of theorems, because really in Calc 3, those details are not that important. If you really are interested in that, you take higher level math classes where that's the purpose. In this class, we're trying to understand some how to do calculus in 3 dimensions so we can use it in other courses, or we can use it for fun. So let's do one more example. So I don't want to do the exact problem that's on the homework, because that would steal the joys from you. So what we're going to do is we are going to do a slightly different one. Okay. So here we go. This is a standard example. So let's compute this triple integral. Where the function no matter what you plug in, it spits out 1. And D is the cone given by. Now, imagine, what is a cone? So we're going to draw a picture of this in a second, but let's imagine, you guys all know what an ice cream cone is. So we'd like to think of it in that sort of aspect. But more particularly, this is a special kind of cone. So it's inside. Okay, where D is, let me state this a little more carefully, because I'm sort of being, let's be much more careful. So D is the region, oh boy. So D is the region. So inside the cone given by phi equals, we need an angle here. So let's say for the pi over 6. And the sphere. So how do you describe a sphere? Well, a sphere is very easy to describe in spherical coordinates. It looks like a phi, so let me. Did phi again. Again, I should be fired. The equation of a sphere is nothing more than rho. And what do we want the radius of our sphere to be? Let's suggest that it's 4. So let's try to draw what this might look like. Again, it's not going to be the easiest thing for our imaginations. It takes some practice to get this, but let's imagine I have sort of my, let me do it like this. So let's imagine I have my X, Y, and Z coordinate system. So don't forget, even though, if you remember on Monday, I messed this up slightly. I had a typo. This is X, this is Y, and of course this is Z. So remember, phi is the angle that is made with the Z axis. That's phi. So essentially what we're doing is, if we take different color here, what we mean by that is we mean phi is some particular value. So let's try to get this as symmetric as possible. So this is our cone. This is what an ice cream cone looks like. Again, it's not perfect at the origin, but we can try to make it. So this is my cone. Again, ice cream cone. We can sort of try to give it the illusion that it's three-dimensional. Now, again, it's worth repeating what I've said numerous times since we started this kind of stuff. With most of these double and triple integrals, the integrations themselves are not what are difficult. It is setting the problem up properly. And what that often entails is, how do you describe the domain and how do you get the equations for the domain? Now, we also have a sphere And we want to know where these things, quote unquote, intersect. So what is going to happen? Well, imagine now I have a sphere. So let's get a different color. Let's say green, maybe. All right. Now, this cone, again, you imagine that it goes vertically forever and ever and ever, right? So this cone is sort of, I didn't give it, notice all I said is that it's all the points that are at this angle from the z-axis, pi over 6. That's all it is. So you would imagine if you see my little pen on the screen, it goes on forever and ever. This cone is going to go forever and ever and ever, unless I cap it off by something. So what I'm saying is now I have some sphere. It's not the best. So maybe what I'll do is I'll try to draw a circle. Instead, let's see if we can get this to work. Let's see if we can. That's not going to get the job done either. Well, let's see. Can I drag? There we go. I want to stretch this thing. So what I'm trying to do is I'm trying to draw. Okay, this is close enough. Let's get this a little closer. So imagine now I have some sphere, although this is not as accurate as it could be. I wonder if they'll let me erase just some of this. Probably not. They're going to erase the whole thing. Darn it. How did I know? Trying to draw this so it's a little more realistic. It's not really working. Okay, that looks a little more realistic. All right, so the idea is, though, what we're interested in is the area under this sphere. So remember, if I take, you have to imagine this is some sphere. And so the area, or excuse me, the region I'm interested in is this sort of ice cream cap. This is what we're interested in. We're interested in the area inside the cone and the sphere P equals 4. So here's how I would like you to think about this. What you should do is you should think about this as sort of the following. So the region is an ice cream cone with a scoop. Does that make sense? Maybe? I don't know. So it's not just a cone, it has one scoop sitting on top of it. Does anybody have a question about this? A better thing that I would encourage you to do is go to GeoGebra and see if you can get it to graph this. You know, it'll be much more symmetric. You'll notice I'm doing the best I can with this sort of pad and trying to look at one screen, draw without looking. It's very different. Okay, so what's interesting though is you need to figure out what these sort of intersection points are. So let's draw this again. Sort of imagine what our solid really is. What color did I use for that? Blue. Yeah, okay, so blue and green. So let's just sort of draw this thing one more time just to remind ourselves what it looks like. Whoa, that's a little more steep than I want it to be. Honest to God. So this is sort of the region we're interested in. And then we have this sort of spherical scoop of ice cream on top. So what we're essentially going to do is we're going to find the volume of this creature, because when we integrate over this region and the function is 1, that's what we get. Okay, so this is the part where you have to, again, this is not easy to learn. This is going to require a heck of an effort. So how did I always tell you I like to do this? Well, I like to write down my 3 integral signs, and then my function, which is just 1. And then I am going to do what? Well, I'm going to use spherical coordinates. Why am I going to use spherical coordinates? Well, first off, the first sort of flag to use spherical coordinates is if you look at the way I stated the problem, I'm actually giving you things in spherical coordinates. I didn't write anything in X's and Y's. I wrote everything in terms of spherical coordinates. So this is going to be 1, and then instead of dv, we'll remember my spherical coordinates are r squared sine of phi, or excuse me, not r, but rho, right? And then this is d rho, this is d phi, and this is d theta. And so I want to remind you, because it's important, that this whole ugly thing, this is the volume element. That's what it is. Okay, now what are our bounds? Well, just like I told you last class, the way I like to do it is I like to work inside out. So my first variable is rho. And so what I'd like to do is ask, where does rho begin and end? Where does rho start and where does rho end? And if we look at this particular problem, we have that it's already given to us. So I'm going to write this in blue. So this is 0 to 4. So what does this mean? Well, you could say I got 0 to 4 because I told you in the beginning of the problem. I said rho equals 4. So that means my radius is extend from the very, very origin all the way up to the top of my sphere. Another way to think about that is if you look over here at our cone, where do the points range? Well, they start 0 distance from the origin, and they go all the way to the tip of the sphere. So that is 4. Okay, now what's phi? Phi variable is the variable. If we go to the previous page, you will remember, and even from the last lecture, phi is the angle from the z-axis. So let's get another color, maybe pink. So phi is this angle. The angle from the z, I said the x-axis, the z-axis to the solid. And we know that that is fixed. In fact, that's how our cone was described. And so what does phi range from? Well, phi, by definition, is ranging from zero to pi over 6. And then last but not least, where does theta range? Well, if you remember, theta is, if you go back to the previous page, and I'll write on, theta is this angle. So let's get another color. Let's say, we'll get, I don't know, how about red? Theta, if we go down here, theta is this angle. in the XY plane. That's theta. And so our cone is full, which means in order to describe the whole cone, we have to let theta range all the way around the circle, or excuse me, generate the circle. Another way to think about that is if I take my cone and then I take any horizontal slice, if I slice it with a plane that's parallel to the XY axis, what are my cross sections? They are all circles. So in order to create a whole circle, I have to let theta range from 0 to 2 pi. If you compare this to the example we did last class, remember we took half of that rod, and so we only let theta range from 0 to pi. So now we're going all the way around. So pardon me while I go lean to the next one. So that means that our bound here is going to be 0 to 2 pi. So this is fun. Does anybody have a question? Let me give the standard annoying O'Grady disclaimer, and that is you ain't learning this in 5 friggin' minutes. You just ain't. It takes a lot of time to learn this stuff. Thankfully, there's YouTube videos, there's textbooks, there's lots of free resources for those of you who really want to learn it. You gotta do that. It's not something that most humans learn in a short amount of time. Does anybody have a question? All right, so I've done this before. I'm going to do it again. I am going to integrate, and I'm going to write the integral variable that I'm going to integrate out, this iterated integral. I'm going to do that one in a different color first. So I'll put my first 0 to 2 pi. You'll notice that there's no theta, so we could have integrated that out right away, but let's go slow. So the first thing I'm going to do is I'm going to integrate my rho. So I'm going to take a different color here. Maybe I'll take green, looks lovely. So what is my integral if I integrate rho? Well, I get 1/3 rho cubed from 0 to 4. And if I integrate that variable, what's left is my d phi, and then my d theta. So does anybody have a question about this? Now, again, the better you are at this, the more you've done, you'll realize I could have integrated out that theta because there's no theta anywhere. I could have killed that bird earlier. And in fact, let's do that now. What is this? This is, there's no theta, so I'm just going to integrate it, and I get 2 pi. And then you're left with 0 to the pi over 6. And then this is sine of phi. And then this is times something. What's it times? This is times nothing more than 4 cubed over 3. So what is 4 cubed? That is 64 over 3, and that's d phi. Well, I don't need the d theta anymore because I integrated it out. So you might take a moment to think about that. So let me put a little comment around this. So what is happening here? Well, the integral from 0 to 2 pi of just d theta equals theta from 0 to 2 pi, which is 2 pi minus 0, which of course is 2 pi. So that's how I'm getting that 2 pi out front. So think about that for a second. If you have a question, please let me know at your earliest convenience. While you're pondering, if you have a question, did any of you guys watch that Looney? We don't even get to talk about this because we're not in class. We could talk about, what's his name? Joe Exotic, the tiger guy. Have you guys watched this yet? That's some incredible television. Right?
I don't know what the heck that is.
What do you mean? I'll tell you what it is. There's
Keep
some Looney
talking
people
about it.
out there. I don't know how a man like that, who doesn't seem to be the brightest, I'm not quite sure how he figured out to get to make a living about it so long. What's even more fascinating, not just him, but all these other people, him and someone has a message. What could it be? Ha! That's funny. This is true, Carol. Well, that's what I was going to say. What's most fascinating, my friends and I have talked about this, the most fascinating thing of all of it, excuse me, is that not just him, but that Doc dude and even Carol Baskins, like they have figured out to get all these people to basically work for them for nothing. They all just work 24 hours a day, 7 days a week for like $100. It's fascinating. So we see we're all watching pop culture insanities. Okay, we have to finish this integration. There's a 64/3 out there. By the way, hold on a second. This is fun. Ha! Okay, that's better. It's brighter. Oh! No, I dropped my pen. I had to turn the light on. It was a very weird feeling. All right, so 64 times 2. Well, what is 64 times 2? That's a beautiful number. It's 128. So let's go to the next page and think about how we could finish this. Ooh. So what does this come down to? It comes, I'm using the wrong colors. So this becomes 128 pi over 3. And then the integral is 0 to pi over 6 sine phi d phi. Now, how do you integrate sine? You integrate sine, it's negative the cosine. So this is 128 pi over 3, and then you get negative the cosine phi from 0 to pi over 6. That's kind of sloppy notation. And so what do you get? Well, when you plug pi over 6 in and you plug 0 and you get different things. So what I'm going to do is, since we're all sort of in Calc 3. Uh-oh, Grandma's here. Did you guys hear that? Grandma's here! Yeah, don't laugh, Emily. This is what we're at. I couldn't imagine, like, Amy's a teacher, but what if she had like a job where she wasn't a teacher, where she was had to work a 9 to 5. I don't know how we'd get anything done. 2 screaming kids, you know. So anyhow, if I'm gonna switch this, I'm gonna write this as cosine of 0, because there's minus a minus is plus, and then this is minus cosine of pi over 6. Now, if you go back to your days as a student in trigonometry, you learned that the cosine of 0 is 1, and the cosine of pi over 6 is what? Well, the way I like to think about this is I always remember that sine and cosine are always the same at 45 degrees, and that's 1 over root 2. So what is the cosine of pi over 6? Well, that's actually square root of what? Square root of 3 over 2. So again, if you don't remember this, you just go to the Google machine and you say, do I really remember these things? And you might go to the unit circle and you say, what is, of course, the cosine of pi over 6? And you say, oh, yes, it is. It's the square root of 3 over 2. And so you're happy with that. Does anybody have a question about this? That's one way to write your answer. Some people, I bet you if you went to the integrals on maybe Wolfram, they would write it slightly different. They would probably pull that 1/2 out, cancel it into 1/28. But that is your answer. Does anybody have a question about this? That was wowzers, huh? Okay, so going once, going twice. Okay, so let's look at some applications of this stuff. Does anybody have a question, comment, concern? So an important application of integration. Notice I'm just saying integration because we're going to kill a bunch of birds with one of the same stone. So one of the things that we can use integration for a tool is to calculate mass. Now, when I say mass, you're going to say, what do you need to calculate? Things have mass. It's fixed. Well, okay, fair. But we're not using mass in the most basic sense. We're talking about things like center of mass or maybe center of gravity, which you raising your hand, Emily, or are you just, okay.
My parents left the house and they took one of our dogs and not the other one.
Okay.
And
So
the one freaking out and they just got home.
Is that like why my kid is we get like that when one of the kids gets to go and they get stuck? It's chaos.
Yeah, it's literal chaos. Yeah.
I know. I know. That's funny. Okay. So you might recall. Now this is going to make your head spin because we've been using sort of this letter twice. So in physics, I guess I should learn how to spell. This is not a physics class, so we're not going to derive all this stuff. But you could. In physics, we learn that density is equal to mass over volume. Right? That's sort of the definition of density. So it's convention, and this is going to make you mad because you're going to say, "Rho, we just used that." To use letters rho equals, of course, m over v. So here is a very important thing that you're going to do, and we have to make note of it, so we'll put a caution. And then only as I could say it, this ain't the same rho. as in spherical coordinates. So this is going to sort of, context is key. So, you know, most importantly, what we need to understand is here, rho is density, and it often is a function. This shouldn't surprise you. Imagine, you know, take something as basic as this pen I have right here. This pen has a density, but is it uniform? And the answer is no. I mean, if you look closely, this pen, first off, its design is not uniform. It gets narrower at the tip. It's likely going to be, I guess, quote unquote, heavier up top because it's back here, it's hollow. And then if there's ink, maybe the ink is only up to here now. We would imagine that the density of this particular pen is not uniform. So it varies. It varies along the horizontal axis, if you will. I mean, you could give examples of any, not any, but lots and lots of objects that their density is not uniform. Imagine an airplane or an automobile. I mean, where's an automobile more dense? In the front where the engine is or in the back where the engine is? Of course. It's going to be more dense there than in the rear seats, where, especially if nobody's sitting there. So if, you know, if I have a satellite and I'm throwing it out in outer space, maybe it's just this big sphere. We'll assume it's a sphere for the sake of argument. There are probably portions where there's instruments on that satellite that are quote unquote heavier or have more mass than other points. And so if we want to understand where and how the mass is distributed and how dense it is, so that if it's, say it's rotating, it rotates in a uniform and non-chaotic manner, we have to understand these. And the thing to keep in mind in all this, back to the pen, is how do I balance the pen? Would I put my finger right in the middle to balance this pen? And the answer is probably not, because of its design. However, if you had a dinner plate, you would imagine that you'd put your finger right in the center of the dinner plate if you wanted the plate to balance on your fingers. Does that make sense at all? A little bit? So density is a very important sort of idea, and it comes down to integration. So that's kind of where we want to talk about right now. Does anybody have a question or a comment about this? So what does this mean from the previous sort of page? So this means, I thought I switched this. So this means the mass of an object is often given. So let's put object in quotations. Is often given by an integral. So if we're in one dimension, what is the mass? The mass is often an integral from A to B of rho x dx. So that would be the mass of a one-dimensional object. So what do you envision as a one-dimensional object? Imagine like a thin line, like a wire, or perhaps a rod, a metal rod that's non-uniform. Okay, so what is, in 2 dimensions, what is mass? Well, in 2 dimensions, the mass would be a double integral. And so that means your density, it is possible that your density is dependent on where you're located on said object. So that would be 1 dimension, that would be 2 dimensions. And then, of course, in 3 dimensions, it is possible that your density is dependent on all 3 spatial dimensions. Does anybody have a question about this? Now think about this. Look at this equation. Every one of these, let me write it on the side just to give you some intuition for this. Remember, what are we saying? Well, if density is equal to mass over volume, that's the same thing as saying that mass is density times volume. And so if we're imagining these incremental changes, if we're imagining how this might work, you can see if you would set up a Riemann sum to compute mass, how it would turn into an integral of this form. I would actually encourage you to do it. And perhaps even in physics, you got to see a little bit of that derivation, or at least the intuition behind it. Does anybody have a question about this? Okay, so Carol Baskins runs a call. I love it. Okay, who has a question? Oh,
I have a question, but I'll remain behind after the class is over.
okay. You sure?
Yes.
It doesn't have to do with this?
No.
All right. Okay, so breaking news. All of Pennsylvania required to stay home. Boo. All right. So here we go. Here's where the fun ensues. So another important application here's another question we might ask. So we might ask, how do I balance an object? Now notice I put balance in quotations. So another way of thinking about this, another sort of intuitive question would be, where do I put my finger to balance said object? You can imagine that this is clearly important in something like engineering. It's important in physics. As I said, one of the, and I showed you this video, I believe, last semester in Calc 2. Remember, there was this astronaut, and he was taking a deck of cards, and he was showing that if you're in without gravity, if you spin it one way, it spins in this very nice, nice, calm motion rotation. But if you try to spin it along another axis, it gets all discombobulated. And that has to do with some ideas from physics. And if you want to understand that, you have to start with these things like center of gravity, center of mass. And to do that, we have to start with the baby stuff. So what we define is the quote unquote center of mass. So what we want to do is we want to define a concept so that it sticks with our intuition. What do I mean by our intuition? Well, you guys all remember, at least as a child, you would go to a playground, you would see a seesaw, you know, where there's a pivot and it goes up and down. And if the kids weigh about the same weight, they can alternate back and forth. Now, how would you get it to balance? It only balances if the kids would weigh the same amount. If you had one heavier kid than the other one, you couldn't get nice uniform motion unless you forced it. So again, I don't want to spend too much time on this. These are things derived or left for physics class. I mean, I guess we could derive them in here, but it's not how we're going to do it, because we're more worried with being able to compute these things than we are exactly where they come from. But you guys know how to do it because we've done where they come from a trillion times with Riemann sums. So this is not anything new to what we've been doing for the last 3 semesters, albeit a slightly different variation this time. So in one dimension, we define the center of mass as follows. So we typically use this notation X with a bar above it. And we're going to define it to be capital M. And this is why most books do this, and it's sort of misleading, but that's just a convention. So you have to understand that there's a capital M and a lowercase m. And what is capital M? Capital M is sort of what we call the moment. And that's an integral. And it's a weighted integral. We're taking the density and we're multiplying it by the variable. So the fancy word for this is weighted integral. And little m is the mass. And so we know what the mass is. That is just the integral of the density. So let's remind you of exactly what's happening, that there's difference. So this is capital. And this is lowercase. This number right here, this is called the moment, or specifically the total moment. And of course, this is the mass. Now, again, if you'd really like to see where these integrals come from, you draw a picture. You imagine you have some beam, which you can imagine is, I don't know, and then you chop this into n pieces. And each one of the n pieces has a mass. Each one of the n pieces has a density. You use the density formula, and then you get a Riemann sum. And then if you let the number of the chop up go to infinity, the Riemann sum becomes an integral. Again, I hesitate to go through all that because we've done it a gazillion times since Calculus 1. You did this with area. You did it with volumes in Calc 2 and arc lengths. and we did it with pressures, and we did it with, I mean, what else do we do with? Oh, the solids of revolutions. And then in here in Calc 3, we did it a bunch of times. So, and we're going to do it again when we talk about things like work, which is another term you may have heard in physics class. So I have to pick and choose what we get specific involved in and what we don't. Okay, so sweet. So what this number does is this gives you a way of determining where to put your finger to balance something that's not. So even if you look at this pen, clearly since the pen is thicker, it's hard for you to see. But if you look at this pen, it's more dense towards the tip. And so my finger to balance it is not in the center, it's more directed in this way. It's hard for you to see that, but it in fact is true. Ooh. Look, it disappears. Ooh. All right, this is fun. Are we having fun yet? Okay. So now we can write these formulas down. They generalize to 2 and 3 dimensions very easily. So what is it in 2D? So what does this mean? This means a plane region. So if we have a plane region, imagine a plate. Well, a plate is given by 2 variables, x and y. So we have to imagine that there's going to be 2 of these quote-unquote moments that we have to determine. So here we go. So the center of mass is no longer 1 point, it's actually 2 points, which we'll call x bar and y bar. And we're going to have very similar expressions. What are x bar and y bar? So x bar equals the following. Now this is going to seem a little counterintuitive. I'm going to write this as capital M sub y over lowercase m. Now what is capital M sub y? Well, this is, let's write this a little cleaner. Let's write it 1 over m. By the way, m here is still the mass. And so what is this integral? What is m sub y? Well, that means we're going to fix. What we'd like to do is we'd like to ask ourselves, if we imagine sort of fixing a variable, like imagine you have some plate, and you say, okay, I'm going to fix a point, and then I want to ask, how do I balance it along one axis? And then you could ask the opposite, how do I balance it on this axis? Another way of thinking about that is if you have some plane region, and if I were to balance it on a pen, what would happen? How would it rotate? And then if I balanced it, if I just said I was going to balance it the other way, how would it rotate? This is kind of what we're trying to think about. And so now, what is this m sub y? Well, this is going to be a double integral. So this is over your domain, whatever it is. And then you're going to take your density and you're going to multiply it by x. And then, of course, you're going to have the analogous formula for y bar. So what is m sub y? M sub y is the moment with respect to the y-axis. And then, of course, m sub x is defined similarly. So one of the things that students often have is you say, well, why is it called m sub y if there's an x in that integral and vice versa? Well, again, you need to think about that. You need to draw pictures. You need to convince yourself, why would we say that this is called the moment with respect to the y-axis? And so I want to do an example, so I'm not going to state this in general. You can look it up. But in 3D, so in 3 dimensions, so this is a solid. We define the center of mass to be x bar, y bar, z bar. So it's a point in space. And so here we have 3 moments. So the first moment, if you want to do for x, you might have x bar equals myz. Notice that there's patterns to how these things work. So now you have a triple integral. And those subscripts tell us what? Well, they tell us what letters, and one way to think about it is do not show up in this integral. And I'm not going to write the other ones down because they're all, the pattern is the same. You can find it in your book. Because we've basically just written down a bunch of scary formulas, and we have to do an example so that we can actually see how this stuff is used. Does anybody have a question? You can look this up. It's not hard to find. The textbook has it, all this written, but I feel like we've written this enough times. Hopefully you see the pattern. Hopefully you use the context clues. So let's do an example. So if you look at homework 10, I give you 3 questions about this. The first one, number 6, the density is 1. And you can also use symmetry. If density is 1, symmetry is a very useful tool. So let's give you some, do an example and then give you some hints before we go. Does anybody have a question about this particular stuff that we just wrote down? All this scary stuff.
That previous X bar, is there still 1 over density?
Yeah, so be careful how I wrote that. I was maybe misleading. Notice I said X bar is, it's this moment divided by M, where this moment is given by this. So notice this, I wrote it down. I mean, this is not incorrect the way I wrote it. It just.
I gotcha, I understand.
And then again, the key observation to make is look where the subscripts are y and z. You see an extra x in the integral. And then if the subscripts were x and z, right, then there would be a y in the integral. Does that make sense? And again, it's you can either memorize that. Well, actually, you don't have to memorize it because I'm not going to ask you to memorize it. I'm going to ask you to solve problems so you can easily look it up. But a better exercise for your learning experience, and I know you're not going to want to maybe do this, but if I were you, what I would do is I would, the case in 3 dimensions is a little more complicated. But if you go in 2 dimensions and you just draw some arbitrary region in the plane, and ask yourself, just even if you assume that the density is even, ask yourself why these m sub x's and m sub y's are useful. And ask, think about it in terms of what we call them. We call them these moments. And then think about objects rotating or falling out of balance. It makes it a little easier to understand intuition for these formulas, I think. I mean, I don't know, maybe not. Sometimes maybe it's hard for me to to remember how little of intuition there is behind some of this. Most of you haven't seen that much physics and stuff yet. So maybe your intuition is lacking, where I'm so used to doing this stuff all the time that my intuition is like, oh, it's clean, it's obvious. Here's a pencil, we want it to balance. Okay, so let's do an example. If I'm looking at the homework, like number 6, for example, the first couple problems, A and B, these are just, you could use calculus, but they better match your intuition. So let's look at some example to help you with this homework assignment. So let's say the first one, we have let's compute x, y, so the center of mass for a disk of radius 1 with constant density. So let's just say our rho, no matter what we plug in, is just a number. We'll say 1. Make our calculation easier. So how could we do this? Well, we need to compute 2 things. So let's get m. So I guess I shouldn't write equal sign. So let's be very clear. This is mass m. So mass is just the integral over this region of 1 dA. Now, what is my domain? My domain is a disk. So the domain being a disk suggests that I use polar coordinates. So this is, if I go to polar coordinates, this becomes the integral from 0 to 2 pi, the integral from 0 to 1 of r dr d theta. Again, what is my region? I'm looking at a disk of radius 1 with constant density. I guess I should have said centered at the origin. Okay, so if I integrate this, this is the integral from 0 to 2 pi. If I integrate r, I get 1/2 r squared, so this just becomes 1/2 d theta. And then, of course, if I integrate This again, I get 1/2 times 2 pi. So the mass of my disk is pi. Now, it turns out we just wasted time, because if you use your intuition, you know what the answer should be. What should the answer be? Well, think about if you had a dinner plate, where would you put your finger to balance it? On the center. So I should get x bar and y bar 0. But let's just suffer through the calculations. Does anybody have a question about this? Don't, just because I integrated RDR real quick and got 1/2, you don't have to go that quickly, but you should fill in the details if it's not obvious to you. Okay, so what's x bar then? Well, excuse me, to get x bar, we got to calculate these guys. So what's this creature? Well, this creature, m sub x, remember, we have to do, we could compute m sub x first or m sub y, it doesn't matter. Let's do m sub x. And so this means we are integrating over our region, and this means it's y times rho. And this just becomes the integral of d of y dA. Why? Because rho is 1. Don't forget rho is 1. Now, once again, our region is a, that we're integrating over is a disk. It's a disk of radius 1, so that means we should absolutely go to polar coordinates. So this, once again, is the integral from 0 to 1. Integral from 0 to 2 pi. Now, what is y? Y is r sine of theta. And then what's dA? This is r dr d theta. So once again, we need to remind you of how this works. So we'll use red here. And what is r sine? Well, that is the definition of y when I go to polar coordinates. Does anybody have a question? Isn't this a Okay, so we have an r and an r. So what we can do is we can combine them to get r squared. So this becomes the integral of 0 to pi, integral 0, 1, sine theta times r squared dr d theta. Are we having fun? Okay, so there's a couple ways you can proceed depending on how comfortable you are with this. I am just going to go integrate r out. So as I've done before, this is integral 0 to pi. I'm going to leave the sine theta alone. Now I have an r squared. So I'll be very careful here. I have inside, I have, this becomes 1/3 r cubed from 0 to 1. If I'm if I'm integrating properly, and then I have a d theta. And then of course, when I evaluate that, I get 1/3, and then the integral from 0 to 2 pi of sine theta d theta. Now, unfortunately, most of us never really use, because we're just babies, we don't really think about what's happening here. I could have seen that this problem was over with a long time ago. This integral 0. integrate sine from 0 to 2 pi at 0. You learned that way back in Calc 1. But even if you don't, remember that this thing does equal 0. So might be worth. So this thing is equal to 0, but let's just show you why for those of you keeping score at home. This becomes, the integral of sine is negative cosine theta from 0 to 2 pi. And so you get 1/3, you get -1 minus a -1, and you get 0. And then a very similar calculation shows y bar is equal to 0. And then hence, as expected, x bar y bar equals 0, 0. Again, if you're going to balance a dinner plate and you don't put your finger in the middle, it's going to fall off your finger. Okay, so this problem showed, again, it shows some ideas that symmetry is often your friend. If you look at homework 10, problem 6a is a square. There's symmetry there to help you in calculations. Problem 6c, there is not symmetry, but so you just have to suffer through the calculations. But if you go to 7a, there's some symmetry. The problem with 7 is your densities are no longer uniform. Your densities vary. And then similarly, if you look at problem 8, there's one with uniform density of 1, and there's one where the varying density. So there's lots of shortcuts in these calculations that you can make, provided that you know what you're doing. And the fact of the matter is you guys are just learning right now, so you're going to mess things up. Do you guys have any questions about these exercises? All right, so, you know, this is some tricky stuff. I mean, I'd be happy if you have questions about any of these. If you want to talk about them on Friday, I'd be happy to do that. I would be happy to answer questions via email, or if you want, I can even write up solutions. Now that I'm doing this, if you have a question, let me know. I'll make a little video solution or slides, and I'll send them to you if you want. If I have free time, I don't know, maybe I'll write up or I'll video all the solutions. I haven't decided. Well, I don't know if I'll have time for all that. Do you guys have any other questions? Peter, I know you said you had a question. All right.
Yes.
Yeah, okay. Well, let's, if anybody wants to leave, feel free to leave. I'm going to stop recording now. And then, Peter, you can ask your question whenever you want. All right?
All right.
All right. Recording is stopped.